Hello, everyone, and welcome to today's session on IoT at the Edge with Meadow and .NET. My name is Adrian Stevens, and I'm thrilled to have the opportunity to speak with you today. And as many of you know, artificial intelligence has been advancing at an incredible pace and is transforming industries, and it's transforming the way that we interact with technology. And simultaneously, edge computing has emerged as a critical component in the Internet of Things. And it's allowing devices to process data locally rather than relying solely on cloud services. And so today, we're going to explore how these two powerful technologies intersect. Specifically, we'll delve into implementing TensorFlow Lite for microcontrollers, also known as Lite RT, and we'll do this on the Meadow F7 platform using, of course, .NET. And we'll also take a look at some innovative AI sensors from companies like Useful Sensors, such as the Tiny Code Reader and Person Sensor. And these offer plug-and-play AI functionality. And so by the end of the session, you'll have a deeper understanding of how to harness these tools to create intelligent, efficient, and responsive edge devices. So let's dive in. Edge AI plays a critically important role in modern IoT workflows, and it's experiencing exponential growth. And devices at the edge are not just passive data collectors anymore. They're actively processing and making decisions based on that data. And this is partially due to the shift to the need for immediate data processing and real-time decision-making. Applications like autonomous vehicles, industrial automation, and smart homes require instant responses that cloud-based solutions can't always provide. So let's look into some of these specific benefits. So first, of course, is lower latency. So by executing these AI models locally on edge devices, we achieve that immediate processing of data. And this is crucial for applications where every millisecond counts, such as emergency response systems or, high-speed manufacturing lines. Also, there's the reduced bandwidth cost. Processing data on the device means we're not sending large amounts of data over the network to the cloud. So this saves both on data transmission costs, but also alleviates the burden on network infrastructure, which can be particularly beneficial in areas with limited connectivity. And of course, keep in mind, if these are mission-critical workflows, the edge AI reduces the risk of failure if that network connection goes down. And so this does ultimately lead to reduced cost of ownership, that TCO, and utilizing the processing capabilities of edge devices can lower server loads and operational costs. And by offloading tasks from centralized cloud servers to distributed edge devices, organizations can achieve significant cost savings. So for example, consider a smart surveillance system that uses cameras to monitor for security threats. If the system can process video feeds locally to detect those anomalies and recognize faces, it can respond more quickly to incidents and reduce the need to stream high-definition video continuously to the cloud. Okay, so we've discussed the importance of AI at the edge, and let's introduce the tools to make it possible. And today, we're going to talk about Meadow F7. This is a microcontroller-based system that's going to allow us to do edge AI using C# and .NET. So the Meadow F7 is a powerful and really versatile microcontroller platform and designed, obviously, for IoT applications. It has high performance, has an STM32F7 microcontroller. It's got a good amount of memory, and it's got a really great set of I/O capabilities. So it's really well suited for running complex tasks at the edge. And of course, the standout feature here is that Meadow, of course, supports .NET. So as developers can write applications in familiar languages, primarily C#, but it does support F# and VB.NET as well. And there's a really great ecosystem of libraries that we can leverage as well. And this means that we can use our existing C# skills to develop for IoT. And so by combining the Meadow F7 hardware capabilities with the productivity of .NET, we've got a platform that's really ideal for implementing AI at the edge. And it bridges the gap between high-level application dev and low-level hardware interaction, which enables rapid application and development of intelligent edge devices. So we're going to talk a lot about implementing AI models directly on microcontrollers, but there are some really great, quick ways of getting AI features on IoT. And if you've got a specialized solution, companies like Useful Sensors kind of have some great hardware. And they provide some plug-and-play AI sensors that offer specific functionality right out of the box. Two notable products are the Tiny Code Reader and the Person Sensor. The Tiny Code Reader is a small module that can read QR codes and other types of barcodes, and it's designed to be easily integrated into projects that require quick and reliable code scanning without the need for complex setup or processing. And most importantly, without the need for us to train and execute a model by hand. Much like the tiny code reader, they also have the person sensor, and this module will detect the presence of people. It can identify if a person is in front of the sensor, it can count the number of people, and it can estimate their proximity. And so these sensors will handle the AI processing internally and provide simple outputs that can be read by microcontrollers, of course, like the Meadow F7. And this makes it incredibly easy to add sophisticated AI capabilities to your projects without diving deep into machine learning algorithms. So no training, no deploying, no runtime. It's just there and ready to go. Now, for us as .NET developers, to make it even easier to work with these sensors, we have Meadow Foundation. And Meadow Foundation is a comprehensive library of drivers and libraries for a wide range of sensors, displays, and other peripherals. It provides some high-level APIs, simplifying interactions with the hardware components, has consistent interfaces. It's a great .NET API. It makes it really easy to swap out hardware against an interface model. And of course, it comes with documentation and samples, making it easy to get up and running quickly. And so for these useful sensor devices, Meadow Foundation includes drivers that allow us to integrate them directly into our project with minimal code. And this code sets up the sensor and defines an event handler when a person's detected or when a barcode is read. And Meadow Foundation handles all that low-level communication, so you can just focus on getting your application logic and getting up and running. And so with that, let's dive into a demo and take a look at the tiny code reader. Great, so let's see the tiny code reader in action. And here we have it plugged into a Meadow board. This is a Meadow Project Lab. This is a V4 board. And it's plugged in over the Quick connector, which is a standard form factor for I2C. And you can see the sensor is actually running right away. So you see the blue light is flashing. And this is the default behavior. And so as soon as this thing gets power, it's going to start trying to detect QR codes. And if I put a QR code in front of the camera, you see that light turn green, and that means that it's detected a QR code. So let's see what the code looks like. Let's see what it looks like to use this programmatically. So if we go back to our project here, I've got a tiny code reader sample. And the first thing I want to show you are the packages. And specifically, I want to show you there's a Meadow Foundation sensors, camera, useful sensors, tiny code reader, a long package name. But this is how we bring in the tiny code reader logic so we can consume or communicate with the tiny code reader in our Meadow project. And now it's just some standard .NET code. So notice we have a field of type tiny code reader coming in from the namespace, perhaps the useful sensor namespace. And to instantiate, we just instantiate a tiny code reader object passing in the I2C bus. And if you're familiar with Meadow application development, this will feel pretty comfortable. And then a couple of things to show you. When the app starts up, we can do a one-time read. We can do this whenever we want. So we could trigger this on some other action, maybe a button press, for example, or triggering from a different type of sensor, maybe a motion sensor, perhaps. And we can do a one-time read. And so when the app starts up, it's going to attempt to see if it can read a code, a QR code, and it'll show any output if it does. And then we configure this application to also read continuously. And so we have a code read event, and we tell it to start updating with an interval. In this case, we're asking to update every second. And when it reads a code, we'll see the output. So let's just pull up the output of our application. And if I bring the QR code in front of the camera, we see our custom message, dotnetconf 2024. Really fantastic, a really amazing way to use AI in our applications for QR codes. Again, you can see just a few lines of code, and we can do really effective QR scanning in our Meadow application. So it's time to introduce TensorFlow, and I want to talk about running TensorFlow on microcontrollers, but I'd like to introduce you to TensorFlow itself first. So TensorFlow is a free and open source machine learning library developed by Google. And it's become one of the most popular frameworks for building and deploying machine learning models. It has really powerful capabilities and a really great community. And what you're going to find with TensorFlow is there's a really comprehensive ecosystem. So you've got amazing tools, you've got libraries, great community resources, really targeted at both researchers and developers, enabling people to build state-of-the-art machine learning and easily build and deploy ML applications. It's built for a wide range of tasks, for training models for image recognition, to natural language processing, to time series analysis, to deploying models in production environments. and is built to run on a wide range of hardware. You can run TensorFlows on CPUs, on GPUs, and TPUs. And it's got language support for, a wide range of languages like Python, C++, JavaScript, and of course C#, making it really versatile. It also comes with some really great high-level APIs. It has Keras built in, and this is an API to make it simpler to construct and train neural networks without needing to really dive in and manage the complexities of those underlying algorithms. And so really, it's built for rapid prototyping, rapid scaling, and designed really to deploy in production environments almost anywhere. And the keyword there is almost. Because traditional TensorFlow is designed for powerful processors with lots of memory. So how do we leverage TensorFlow but run it on resource-constrained devices like microcontrollers? And this is where TensorFlow's Lite RT comes into play. And specifically, we're going to look at a detailed version of Lite RT called Lite RT for microcontrollers, which is a version for TensorFlow, as the name suggests, optimized to run on microcontrollers, devices with highly limited resources, and which is going to let us execute our pre-trained machine learning models on microcontrollers. Now, I want to be clear, though, it does have hardware limitations. Not all models are going to run on microcontrollers as is. Models often need to be optimized and quantized to reduce their size and computational requirements. And this brings us to Meadow TensorFlow for microcontrollers. And Meadow TensorFlow for microcontrollers is an integration of TensorFlow Lite RT into the Meadow platform, specifically for the Meadow F7, which of course is going to enable us to run those optimized AI models on Meadow. And note, this is the only .NET API for running TensorFlow's Lite RT today. We'll look at some more code later on in the demo, but I really want to point out here that this is a modern .NET API for Lite RT. And you'll see it's a familiar and modern application. In this case here, we're instantiating a model to detect gestures. And take a look at the code here. We're calling a set data method to give the input. We call predict. That returns an output object, and then we can examine that object to see the accuracy of our prediction or inference. We'll look at this in more detail in a moment, but again, this is a modern .NET API. On other languages, you're often integrating deeply and recompiling TensorFlow to make it work on these platforms, not here. So what's required to use Meadow TensorFlow? So first, you're going to add the Meadow TensorFlow Lite NuGet package to a Meadow project. And this is the package that provides the necessary libraries to run TensorFlow Lite, including that TensorFlow or Lite RT library. Then we'll load our pre-trained model, again, a pre-trained model into our Meadow application. So this involves including the model file in our project or bringing the data in as a byte array. And then we'll allow TensorFlow to load it at runtime. Next, we'll prepare the input data for the model. This could be sensor readings, image data, or any other data that the model expects. Then we'll execute the model with the input data and collect the output results, just like you saw in the previous slide. And that's going to allow us then to interpret the results and use them to make decisions or trigger actions within our application. So now is a perfect time for a demo. Let's hop in and take a look at running TensorFlow Lite on a microcontroller with the .NET and C#. Okay, now let's try running TensorFlow on a microcontroller using C# with Meadow. And here we are again with my Meadow project lab. This is actually the same hardware from the previous demo. Don't worry about the useful sensor that's plugged in, but that won't be part of the demo today. And there's actually not going to be a whole lot to see on the Meadow. Most of the action is going to happen right within Visual Studio. But of course, we could wire this up with a camera and have a more complex demo. We're actually capturing values live and bringing them into our project, which is a little bit of a hint of what we're going to do in this demo. And we're actually do handwriting recognition. I want to show you this. So this code here is actually a clone of the Meadow TensorFlow repo. We're actually going to rename this to Meadow Foundation RT Lite to match the new TensorFlow RT Lite from Microcontrollers naming convention. This was brought out late 2024. And here you find all the source code and the bindings for the RT Lite for Microcontrollers library, as well as a handful of samples. And we're going to run the MNIST digit sample. And that MNIST stands for the Modified National Institute of Standards and Technology Database. And this is a massive database of handwritten digits. And that's been used to train a model that we can use to then give new input data to recognize digits from 0 through 9 in this case. So in our project here, we've got a few things included as embedded resources. We've got 4 test images. We've got a 0, and this is a small one with a very thick stroke. We've got a 2 with a very thin stroke. We've got a kind of chunky, blurry 4, but at larger resolution, and similar with the 6 here as well. So a variety of quality and sizes of sample images. Now, again, this could be run with the camera as an input, but for simplicity today, I want to just have the images pre-baked in our solution. The other thing worth pointing out here, of course, is the MNIST TF Lite file. And that is actually our model. It's our model data. And you sometimes for RT Lite, for microcontrollers, you'll see on other languages, they'll embed this as a byte array in the project. And this is actually fairly similar. It really is just the binary data in this file, but a lot cleaner to load it in as a TF Lite file. Again, we're .NET developers. Like things neat and tidy, don't we? So let's take a look at what it means to run this project. And again, we're back in C#.NET, and you'll see familiar things. So the first thing we do is we create an instance of our model, MNIST digit model. I'll take a look at that in a little more detail, but it's actually derived from a standard class here. And then we load our file. We're going to bring in our model file, our TF Lite file, and then pass in that data into our MNIST digit model file. And then we're going to run our test. So I showed you those 4 bitmaps earlier. So here we're going to load those in. And then we're going to run, we're basically going to classify each of those images. You notice here, model classify image, and we're going to loop through all 4 of them and get the results. But before I show you the output, I just want to show you a little bit of the code here. And to go into our models, actually, sorry, down to our MS digit model here. So this is the class that will actually do the heavy lifting. And this shows you a little more of the .NET work under the hood. Now, this is written specifically for this demo, but this is a really great pattern you can use for other models. You want to use a different model to run inference on your Meadow F7. So we derive from a standard model class. This is part of the library, and we're going to get the results as floats. The arena size here really is just like a buffer. It's kind of the working space, and this might be a little bit of trial and error, but this is actually a roughly good size. 10 by 1024 will probably work for a lot of cases for models that are trained for microcontrollers. Then we've got a little bit of specific logic. You've got an enum for the different digits we want to recognize. Here, this is a little bit of work to normalize our image. This is very standard for machine learning, where the model is expecting a standard input. In this case, it's a 28 by 28 grayscale image. You know, it's made those images of various sizes. Well, this is the code here. It's actually going to resize those images and get them working nicely. So we have the appropriate input size, input data to get reasonable results. And then at the end here, here's that classify method we saw being called from our Meadow app CS file from the Meadow app class. So we resize, basically we normalize, we set the inputs, and this is coming in for each image. And then we just run predict. Okay, I can show that too as well. We'll go to that definition. And this is actually defined in the base model class. And this is where the actual work is done. And again, this is the .NET. You don't have to worry about all the inner workings, the details here. It's a great thing for us since this is baked into the library. This is the code you're going to call, though, to get the output. And again, here we see we get the prediction and then return that value. And if we look at our output, we can see here for our 4 values, our 4 bitmap came back with a 4 with a confidence of 6.3. Our 6 came back with confidence 3.7. And the 0 and the 2. So it actually recognizes all 4 digits. And not surprising, this is a very standard, well-established test, and a really great one to get you started. A really nice hello world for machine learning. And these values here are relative. And so the reason they're different values is not that one is better than the other, but what these are relative values to the other possibilities. And so it's going to run that 4 image against all the possibilities. It's actually going to score whether, you got to score back for a 0, for a 1, for a 2, for a 3, for a 4, etc. And the 4 had the highest score, which is what we want to see because our input value was a 4. And so in that case, the relative confidence was a 6.3 because it's a bit of a unique shape. And again, the 6 is a little blurrier. 6 is close to 5. And so it's not as surprising that that confidence is a little bit lower, but still came back as the strongest result. And so really fantastic. And there you go. We just saw running with TensorFlow on a microcontroller using C# and .NET. Now, the Meadow ecosystem, or Meadow platform, isn't just limited to microcontrollers. If you're using Meadow for a while, you probably think of Meadow as the Meadow F7. But the Meadow ecosystem actually supports hardware across multiple platforms. So in addition to the Meadow F7, Meadow supports single-board computers, like Raspberry Pi or BeagleBone, and the NVIDIA Jetson Nano. Even supports desktop machines via Meadow Linux. And this gives us a lot of opportunity to choose the right hardware based on our needs. And these hardware selections often balance power consumption against compute power. For example, the Meadow F7 can run very easily on battery power, making it ideal for low energy applications or things that are deployed out in the field at scale. But if you need more performance, you can move up to something like a Raspberry Pi Zero or a full-blown Raspberry Pi, or into a BeagleBone, or even the very powerful NVIDIA Jetson Nano. And so again, this flexibility lets us select the right hardware for our Edge IoT project. So we're not going to go into a lot of detail today about training, but I do want to take a moment to make sure that we understand from a high level how we train and deploy a machine learning model to a microcontroller. And again, the microcontrollers are great for running optimized models, but they're not designed to be doing the training directly on the edge. And so to train a model with full TensorFlow, we'll likely begin training our machine learning model using the full version of TensorFlow. It's on a computer or server or in the cloud. And this involves feeding the model with training data, adjusting parameters, validating performance until it meets our requirements. And this brings us to the end of our session. But before we conclude, I'd love to point you towards some great resources. There's a ton of documentation on the Wilderness Labs website, www.wildernesslabs.co. Great documentation, links to a lot of things. I also highly recommend you go to their GitHub, github.com/wildernesslabs. Go to wildernesslabs/Meadow Foundation to dive into the source code. Again, it's all open source for the peripheral driver library, and that's where you're going to find that source code for those useful sensors. If you go to github.com/wildernesslabs/Meadow TensorFlow, well, that's where you can dive into the source code for the Lite RT for microcontrollers integration for the Meadow F7. And of course, Google's got a ton of great documentation as well. ai.google.dev/edge/LiteRT. This is just scratch the surface. We've seen some great hardware, and AI is one of those great areas where we can jump into things quickly with stuff like useful sensors, or we can spend months, weeks, years even studying if we want to become experts at creating algorithms. And what I love about platforms like Meadow and .NET is that we don't have to spend years to learn how to use these tools. But they're an awesome gateway if we do want to go further down. And of course, there's tons of resources out there to go further in AI. Microsoft Learn is fantastic. I love Coursera. LinkedIn has some great courses as well. And with that, thank you so much. Again, let's remember, AI at the edge becoming really important for efficient, low-level, low-latency IoT AI applications. Doesn't mean we don't want AI in the cloud still. Really, a great solution probably be a combination of both. We love Meadow and .NET to make it easy for us as developers to build those solutions. And with that, thank you so much and enjoy the rest of .NET Conf 2024.